My name is Banu. Today I am going to explain the concept of random process in probability theory and stochastic process. Let us go into our topic. Introduction to random process. In earlier chapters, we have studied about probability theory. Probability theory means how we deal with uncertainty. Random variables whose values are not fixed but depends on chances that we take. And now we move on to random variables to random process, which a random process consists of a certain random variables like x, y, and so on, which we are going to be discuss further. Next, let us come to the basic definition of a random process. A random process is a time varying random phenomena described statistically using tools like probability distribution function and density function, correlation and covariance, which helps us understanding and model signals such as noise and message signals in communication. Generally, random process is used to describe statistical properties like density and distribution, correlation and covariance functions, which helps us to understand model of signals such as noise, background noise, and message signals communication in communication systems, etc. Next. What is a random process? Generally, a random process is also called as a stochastic process, is a collection of random variables that changes with time. In simple terms, it is a time varying random signal. Examples for time varying random signals like random process are message signals in communication, background noise in a receiver, variation in weathers like temperature and rainfall, etc. Speech or music signals are some examples of random process. As we said, random process is also known as stochastic process. These stochastic process changes with time. For every interval of time, the value of the amplitude is changes, and the signal behavior changes with respect to time. And next, why do we use random process? We use random process to study signals that change unpredictably with time, such as noise or message signals. We cannot fully know the behavior. Only their statistical properties like average, power, variance can be known. Hence, they are described statistically, not deterministically. Yes, we can describe this random process. Um, we can use this random process to predict or study signals, like the signals which we are don't know. I mean, like which behavior can't be predicted. Those signals we are going to be study using this random process. We can't predict their behavior, but we can go through their statistical properties. We can cross check their statistical properties like average, power, variance, etc. We can check them. Hence, they are described statistically, not deterministically, which we have discussed. Next, statistical description. Because the exact values at every moment are known, we describe the process using statistical measures. As the values are known at every point, we are going to describe this process by using statistical measures such as probability distribution function gives the probability of different values. Probability density function, which is small pdf, describes how these probabilities are distributed. Probability distribution function, capital pdf, gives how the probabilities are different values are given. And probability density function describes how these probabilities are distributed in that signal. These functions tells us everything about the randomness or statistical behavior of the particular signal. By using these distribution and density functions and statistical properties, we can describe about the randomness or statistical behavior of the signal. Energy and correlation. Energy and correlation are also very useful in studying this process. Random process have infinite energy, but they exist over all time. As they exist over all time, they have infinite energy. So instead of total energy, we study finite energy functions. Like correlation function measures how similar the signal is to itself at different times. Correlation function is used to measure how the signal is similar as time changes at different time intervals, I mean. Next, covariance function measures how two random signals vary together. Next, covariance function is used to measure how two signals, random signals, vary together. These helps us to understand the time domain behavior of a random process. By using this correlation and covariance function, we can understand the time domain behavior of this random process. Next, random process temporal characteristics. Basic definition of random process. A random process is also known as stochastic process, as we know, is a process in which a random variable depends on both time and sample space. Time is represented with small t and sample space is represented with s. Time, how the variable changes over time, and sample space, how the random outcomes for an experiment is known, and the time is the x-axis which changes. So a random process is written as x of s comma t, or simply x of t. Here s represents the randomness, sample points, and t represents the time. That means for every random outcome we get a different signal function of time. For every value of time, the random outcomes s gets changes, and we get different signals at different time intervals. uh, as time changes, the signal also changes, as we have discussed previously. Different forms of random process. Random process mainly consist of three forms. Time, when time is fixed, is one, and when sample space is fixed, and when both time and sample space are fixed. Let us come to when time is fixed. You only look at particular instant of time. The random process becomes random variables because only randomness remains. Here, when time is fixed, only uh, only we look at particular instant of a time at particular time interval, how the random process or random mean, like, that signal is going to be occur, and it is represented as x of s comma t1. This shows how the random value of a process at time t1 is presented there. Here at time t1 interval, how the signal behavior is like are going to be observed by using this. Next, when sample space is fixed, you are looking at only one particular outcome, like one experiment. It becomes a real function of time, represented as x of s1 comma t. This means for one specific experiment s1, how the signal changes over time. Like here, when here we consider different time intervals, but the sample space is fixed. For that fixed sample space in interval at different intervals of time, we are going to analyze the signal, and how the output is going to be, by we can verify by using this samples when sample space is fixed. Example for this are waveform of a waveform of one realization of a random signal. Next, when both time and sample space are fixed, both are given specific values, so it becomes a constant, represented as x of s1 comma t1. Here, both time and sample space are fixed, so it almost represents a constant value. Not almost, it represents a constant value. Example, the value of a experiment at specific instant in one in experiment, like at one time interval, that specific experiment, what is the outcome is going to be checked, very observed through this. Next, conditions, representation, nature, and example. When we come to conditions, time variable, sample space, and sample space is variable. When time is fixed, sample space fixed, and both time and sample space are fixed. When time variable, sample space is variable, then it is represented as x of s comma t. It is a random process. Example, random signals. When time is fixed, it is represented as x of s comma t1. It is random variable. Noise at a particular instant. When sample space is fixed, it is represented as x of s1 comma t. Here time function. one noise waveform. When both time and sample space are fixed, it is represented as x of s1 comma t1, which is a constant. Single value of a signal is used to are examples of both time and sample space are fixed. Next, classification of random process. Based on whether time and random variables are continuous or discrete, we classify random process into four types. Yeah, like whether time is continuous or discrete, or random variable is continuous or discrete. We have classified the random process as four types: continuous random process, discrete random process, continuous random sequence, and discrete random sequence, which are known as CRP, DRP, CRS, and DRS. Let us come let us come to continuous random process. Here time is continuous, random variable is also continuous. Example for CRP are voice signals and thermal signals. Next, when we come to DRP, discrete random process, here time variable is discrete and random variable is continuous. Example for discrete random process are daily temperature readings. When continuous random sequence, here time is continuous and random variable is discrete. Examples are switching between discrete states and continuous. Switching between discrete states continuously. Next, last one, discrete random sequence, DRS. Here time is discrete and random variable is also discrete. Digital data, coin toss outcomes at fixed time are some examples of discrete random sequence. Now let us further go into these concepts. First, classification of random process are four types. First one is continuous random process. A random process is said to be continuous if both time and random variable are continuous over the entire duration. Here in continuous random process, both time and random variable are continuous entire the duration. In this, the random variable can take any value within a continuous range for all moments of time. Here, random variables can take any values over all the time period, over all the time. It can take any value or any sample space. An example is the fluctuation of noise voltage in an electric circuit, where the time and amplitude vary continuously. Here, example is considered as a noise voltage in electric circuits, which we can't be predicted, which changes with respect to time, and amplitude also varies continuously. As we can see the sample function of a continuous random process signal diagram, it changes as time changes. It continues, like the signal behavior can't be predicted. No common behavior is observed, like no common curve is observed here in this signal. um, Next, discrete random process. In discrete random process, the random variable takes discrete values, but time is continuous. The random variable can switch only between certain fixed levels while the time progress continuously. Here in discrete random process, the random variable takes discrete values, but time is constant. In discrete random process, random variable is discrete and time is constant. In random variable can switch only between certain fixed levels while time progresses continuously. For example, a digital signal that alternates between two discrete levels such as positive and negative levels but exists continuously in time. Um, when we consider an example, a digital signal that alternates between uh, two discrete levels like positive, negative, but it exists continuously in time, but its values exist continuously in time as time changes. Let us consider this diagram. Here the signal first at a positive peak and next it again fall to negative peak. Here, as time changes, the value of amplitude, mean like the signal is either 1 or -1 at every interval of time. So here it is between either positive level or negative level. Only two levels are present here. Next, in continuous random sequence, a continuous random sequence occurs when time is discrete but random variable is continuous. In continuous random sequence, time is discrete but random variable is continuous. A random signal is defined at specific interval but its amplitude can take any continuous value. Here the random signal is defined at only specific intervals but its amplitude can take continuous values in the signal. It is represented as a set of random variables defined only for discrete sampling instance, such as t, tk is equals to 0 comma 1 comma 2. It is represented for all set of random variables but defined only at particular sampling instances such as 0 comma 1 comma 2. This type is often used when sampling a continuous signal without quantizing its amplitude. Yeah, this process is also used when a continuous signal is when we are sampling a continuous signal without quantizing its amplitude. As we can observe, the function here at discrete values all together are joined, which forms an irregular signal. With respect to time, the signal is also is changing continuously. As we consider this example, graph sample function of a continuous random sequence. Next, discrete random sequence. In a discrete random sequence, both time and random variable are discrete. Here, in discrete random sequence, both time and random variable are discrete values. The signal is sampled at distant discrete time intervals and the amplitude is also quantized into discrete levels. Here, the signal and amplitude are quantized into discrete levels and discrete values. The process is commonly used in digital signal processing. In digital signal processing, we use discrete random process in which both time and amplitude are discrete, are having discrete levels. The amplitude may be represented using two level or multi level quantized levels depending on the application. It is often obtained by both sampling discretizing time and quantizing discretizing amplitude. Here, the sampling can be obtained by discretizing time and quantizing quantization which is discretizing amplitude. Let us come to the model graph. Here, a sample function of a discrete random sequence. Here, at time t, the it is either positive or negative, and with respect to time, the discrete values are represented as here as shown, and the model graph is either positive peak or negative peak. It is varying between those two, positive and negative, and changes with respect to time. And yeah, that's all. Thank you.